Uh, well, enough of that. I would like to get to the speaker today. An old friend, well, he's a long-standing friend and colleague and collaborator. Kent Choquette is giving today's talk on fun with photons. Kent has been at the University of Illinois since the year 2000, so a year longer than I've been here, which I didn't think was possible, but yeah. Kent did his undergraduate degree at the University of Colorado and got his PhD at Madison at the University of Wisconsin. Kent has had a long and storied career doing many interesting things in optics and semiconductor physics, but is probably most famously known for his work in lasers, in a particular type of laser called a vertical cavity surface emitting laser. And I'll let Kent tell you more about that, but Kent, thanks for being here, and without further ado, Kent Choquette.
All right, good morning. Good morning.
Good morning.
Thank you, thank you. I want to, was that too loud? Okay. I wanted to make sure to also thank you for coming out today, because on a beautiful summer day like this in the springtime, there's a lot of other things we could be doing, and so I really appreciate you coming to hear a little bit about something that I'm very excited about, and that is photonics in general and lasers in particular. So what I'd like to do, my name is Kent Choquette. As Scott said, I'm a faculty member in the Electrical and Computer Engineering Department. My office is right next door in this building to our south, which is the Micro and Nanotechnology Lab. Inside of that laboratory is one of the world's best academic clean room laboratories, where my students do a lot of work, have a lot of fun, and so later on in my talk I'll show you a little bit of what my students do and tell you a little bit about my research. But what I really want to do is to motivate my research. And so I'll start off by saying, how many of you have used the internet this morning? Everybody. We consider it like oxygen. It's something that we just expect. So that means that you used many, many lasers. You just didn't know it. And in particular, you used a laser that I'm very excited about, what, as Scott said, the vertical cavity surface emitting laser. And I'm showing you here some pictures of these lasers. We call them VCSELs because in engineering, we are butchering the English language by making up lots of new words that are the first letters of a bunch of other words. So, then the reason why I'm showing you these pictures are you could not see these with your eye. All of these structures are really, really small. Something on the maybe a little bit larger than a piece of sugar, but not much. And so you wouldn't be able to see them unless you had a microscope. So I'm blowing them up so you can see them. These were all made over here in this building by my students. So let me first tell you, this talk is fun with photons. So what is photonics? Photonics is a term that we use for the application of light. As many of you may know, light can be considered either a wave or a particle. If it's a particle, we call it a photon. We usually think of it as waves, and I'm not really going to get into that today. That would be another talk. But in my research area, the discrete nature of light is important, and so we call this photonics. And photonics today is what I would call the infrastructure of the internet. That everything you do on the internet is enabled, happens because of the ability that we've developed over the years of being able to generate, manipulate, and detect light. So that's what that's my introduction of what we're going to of why I want to talk about my research. But let me first kind of get us calibrated, because I'll throw out things like sizes and wavelengths and things, and so we need to kind of understand a little bit what we mean. So first thing is we'll look at this from the point of view of the length scale. So we can think about a meter. That would be, I'm something a little over a meter tall. So that's we know what that is. If we consider a centimeter, that would be the size of your little fingernail. That's about a centimeter. If we go down to 100 microns, that sounds pretty small, and in fact it is. For most of us, 100 microns is the diameter of a hair. Okay, so now we're down to where we can see it, but we can't see much detail. All right, if we go down to a micron, okay, this is 10 to the minus, the length scale would be a power of 10 raised to the minus 6, which means 0.000001 meter. All right, that would be the size of something that would, give us a disease. This is, for example, that's on the order of a size of a cell or something. And then when we get down to a nanometer, 10 to the minus 9 meters. Okay, so I'd have to say 8 zeros, 1 meter. That's really, really small. This would be the size of, for example, perhaps the diameter of a DNA strand, or, frankly, the size of a layer within a modern transistor. It would be the size of a layer that we would be using in engineering to basically make devices. And in my research, this is indeed, we are growing materials, we're controlling materials, semiconductors, down to the nanometer or below scale. So this is why we call this the nanotechnology lab next door, because we're really working with small things. But small things can have a big impact. All right, let's talk about light. I mentioned light can be considered a wave or a particle. So if we consider it as a wave, this would mean that in time we have an oscillation of electric and magnetic fields. And so we can talk about the wavelength, that is to say, when the wave goes through one oscillation. So, if you think about the pond, you chuck a rock at those darn geese that are swimming there, you would see the waves, and you could imagine measuring the distance between the ripples in the water, and that would be the wavelength. And that would be in a pond, a couple of centimeters probably. So, but light has a wavelength, and it can vary, actually vary all across the length scale. So if we were, let's start really long. If we talk about really long, so if we had a wavelength of 100 meters, that seems like a really long wavelength, but that's the wavelength of your AM radio. So when we don't listen to AM radio anymore, but some of us who have white hair like me remember AM radio, and that's the wavelength. Well, that's really long. If you think about it, your car, if it detected AM radio, it had an antenna, and that always helped it. And that antenna was not, it was maybe a half a meter or 2 meter in length. The longer it is, the better reception. That's because these are really, really long wavelength waves. All right, well, let's get shorter. Infrared. This is the electromagnetic regime that I liked working in, because it turns out, as we will talk, that the light that we use in the internet is actually at 1.3 and 1.5 microns in wavelength. That doesn't mean anything to you, but what I can tell you is that wavelength is in the regime where mosquitoes can detect. So if you're a mosquito and we're walking around, we're big heat sources, they see us that way. So so in some sense infrared is heat, but we're working on the shorter side. Now, this tiny little regime right here is what we call the visible wavelength. That's what these wonderful things called eyeballs that we have in our heads can detect. And we think that that's all there is to light, but actually it's a really narrow spectrum. And it also is challenging to make technologies at those wavelengths. But so I wanted to point out that notice how the regimes here that we're using for communication, radio communication, infrared. But what we see is just a tiny little bit. Then we have the higher energy stuff, things that are high enough energy that they can be, they can harm us. X-rays, gamma rays. The gamma rays are the things that we really are happy. Some of these high energy radiation that we're really happy that we have things like ozone in the atmosphere to shield us, so that things like, human life can exist on this planet. So today, I'm going to really be focusing at about 1,000 nanometers, about 1 micron. Okay, so now we're calibrated. So then what I want to ask is, what is your most precious possession? So when I ask this to my undergraduate classes, there is no question. Because when I come in the mornings, they're all like this. You know, it used to be I would come in and they'd all be talking to each other like this. They're communicating with each other, but they're doing it through their smartphones. So I want to use the smartphone and show you in particular the photonic technologies that go into this, just briefly discuss some of the technologies that go into this phone. I'll be focusing kind of on the photonic technologies, and I also want to try to make a link back to the University of Illinois. So here's the question. You go to Yellowstone. Yellowstone is one of my favorite places. My sister works there. So we didn't get to go last summer, but 2 summers ago we were there. And on the way out, we had the opportunity to see a mother grizzly and her 2 cubs. Well, what do we have to do? We immediately stop, whip out our cell phone. Of course, when we stop, everybody stops. If you've ever been to Yellowstone, there's lots of traffic jams. And we take a picture. Okay? There we go. We got a picture. Well, of course, my wife, she wants to put this on Facebook immediately. So she's working on this, and it goes off to Facebook. And pretty soon, you know, the rest of the world knows that we saw a mother and 2 cubs at Yellowstone. So the question is, how did that picture, how did that image that you took on your phone, how did it get to Facebook, and how did it get spread around to the rest of the world? I'm not saying that my wife has that many followers, but in principle, all around the world. Does anybody know? Is it radio waves? Okay, because, you know, here's our cell phone. What did these cell phones talk to? Cell towers. So what happens when it gets to the cell tower? Just bounces to the next cell tower and the next cell tower? That's what we're going to talk about. But let me first take a little side detour here and mention that Facebook is one of these companies that we now call an internet company. And essentially, internet companies are in the business of acquiring and selling data. We are in the age of, we're in the information age, and sometimes we call the years now big data, meaning that data is everything. So what does that mean, data? Well, data is, to an electrical engineer, is zeros and ones, and it's stored somewhere. So when I ask, how did that picture get from your phone to Facebook, what I'm really saying is, how did the digital information that we use to represent that image, where was it stored? And the answer is, it's stored in what we call data centers. These are buildings that are sprouting up all across the globe, usually in colder parts of the world. And these are big buildings that have no windows, some doors, and big air conditioners. And they're just filled with computers. And those computers are where your Facebook and every other thing that's stored on the internet, when we talk about the cloud, that's where the cloud is within these data centers. All right, that's great. So these are big buildings with computers, and by the way, I just want to point out that these data centers are the fastest growing use of electricity on the planet. So when I started this morning by saying, how many of you use the internet? And you all did, and we kind of expect it like oxygen. It's not. There are costs, and one of the costs is the energy usage that we're using to support the internet, and it's becoming non-trivial. Meaning that if you look at how it's expanding and how many power plants we'd have to build to keep up with the rate of expansion of the internet, it's not sustainable. So we have some issues, which is why hopefully there's still research to be done in this area. Okay, so data centers have all these computers. The question is, how are those computers connected together? Because they want to talk to each other. They want to share the data. Well, you might say, good old copper. We'll take a piece of conductor and we'll connect all these computers together. And you would be wrong, wrong, wrong. And the reason is because we don't have enough metal on the planet, quite frankly, to connect all these computers. Furthermore, the building would need to be much, much bigger just to hold all those cables. We got to have a more efficient means for transmitting and distributing data. And the answer is we're going to use fiber optics. We're going to use light. That's why photonics is so important in the internet. Okay, so what we're going to do, if I ever get past my introduction slides, is we're going to look at the cell phone and see what's inside with a focus on photonics and a kind of a sub-focus on why it's important, what the ties are back to the University of Illinois. Then the second part is we're going to talk about the internet. Okay, and we're not going to talk about, I'm not a computer engineer, I don't know very much. I'm a device person. So what we're going to talk about is the physical infrastructure of the internet and how it's enabled by photonics. So that's how I'm going to organize my talk. Okay, so what's inside of a cell phone? Okay, now if I was a really good speaker, I would take my phone right now and I'd break it and I'd open it up and show you what's inside. I'm not going to do that. I have broken phones before, but not for that reason. So but I can go to the internet and I can find some images of someone who did. So if you took your phone, you can break it open and you find a lot of parts inside. And by the way, all the youth in this room, you know, do break someone. Take an old phone and do open it up and look inside. In my day, I looked inside of old radios and that's what got me excited about wondering how things worked. Well, that's what you have to do is break something and see what's inside. All right, so my colleagues in the department who do real electrical engineering, they think in terms of circuits and things. They would say the cell phone is some sort of block diagram with various functionalities. I don't know what that is. To me, I'm a device person. I like to think about the physical things inside that phone and what they do. So, for example, we know that we got a display, we have light coming out at us. So there's an LED in there. There are cameras. We have a display. So you have liquid crystals, and you have a lot of really cool and small transistors. By the way, I should point out, we used to talk about how computers are driving the technology. Today, smartphones are driving the technology. We have more technology. I got more technology sitting in my hand than a supercomputer I had when I was a grad student. I mean, it's amazing how things have advanced. So I want to look at a couple of parts of the cell phone. The first part I want to look at doesn't sound like it's connected to photonics is the microprocessor. There is a computer chip inside at least one, multiple ones actually, inside your cell phone. So if you were to crack open that microprocessor, what you would see inside is something like this. There'd be a little chip, there'd be a big old package because it turns out that the connections are the biggest part of the business of an integrated circuit. But if I continue to break this, I can look at inside of this, there'd be a piece of semiconductor. In this case, it'd be silicon. Silicon is one of the most prevalent, after hydrogen, one of the most prevalent atoms in the universe. And it turns out it has some very interesting electronic properties that we've exploited to be able to control electrons. So today we make silicon circuits on big wafers. If I was to take this wafer and break it, and I'd look at the cross section, I'd break the wafer and try to see on the edge. Well, now I'm down into the micron and submicron scale, so I really can't see this. So this is a magnified image. And what you're seeing here is basically metal. These are just metal layers, multiple layers of metal. And on the scale of our electronic devices, these are gigantic, okay? This would be like from space when we see our cities, basically what we really see are all the roads, all right? Because the roads are very big, especially in big cities. These are the roads leading to what we can't even see on this slide. But if I go and get out my my electron microscope, then I can see that down here I have a transistor. Okay, now a transistor is just something that controls how electrons flow. Well, electrons, that's not a photon. Well, why am I telling you this? Well, there's two reasons. One reason is because these are very important devices, and when I took that picture of the bear, I had to process the image that was collected into electronic data, into zeros and ones. That was all done in this processor. So it is important in this tale of how the picture got on Facebook, but there's another connection, and the connection is directly to the University of Illinois. And if I didn't tell you this, I would be beat by all my colleagues. The transistor was invented in the middle of the 20th century by a team of individuals, Bardeen, Bratton, and Stockley. John Bardeen is the University of Illinois, I would say, is the College of Engineering at the University of Illinois. He's our guardian saint. I mean, this is the connection to Illinois. He was a faculty member here before my time, and he won a Nobel Prize for inventing the transistor. Well, that's not enough. He came here and after playing he was a big golfer, I guess. After playing some golf, he did a second great thing where he developed a theory of superconductivity, and he got a second Nobel Prize. Now, it's great to get one, but John got two. And in many ways, John Bardeen represents how we view engineering on this campus. He was a scientist and he was an engineer. He wanted to know how things worked, and he was interested in how they could be applied. So he actually, when he was here, he was half-time in physics, half-time in electrical engineering. So depending on which side of that we talk about, we consider them ours, but we have to share them. All right, the other thing that ties into photonics is that this transistor utilizes what we call a p-n junction. Now that's jargon that means basically we did something fancy to the semiconductor. But the p-n junction is the heart of every LED, light emitting diode, every laser, every detector. It's the key part. So, you know, yeah, he invented the transistor, but more importantly, he learned how the p-n junction worked. And that's essentially what we've been doing for the last 70 years since then. Okay, so that's the microprocessor. That's John Bardeen. What else is in the camera? What else is in the cell phone? Well, a camera. So, you know, what's really interesting, these things are, you know, we call them a cell phone, but they're everything but a phone almost. But one of the things in there is we have a little camera. Well, how does a camera work? Well, a camera is also actually a piece of semiconductor that now is used to convert light into electrons, convert light into something that we can manipulate on our microprocessor and store and perhaps send through the internet. So the way this works is we have multiple layers here. This is the business end. This is a chunk of semiconductor where we have lots of detectors. On top of that, we'll put some color filters because we see in color. So we need to somehow collect all the primary colors, red, blue, green, and then store it on this chip. So as many of you know, whoops, here we go. So here's that camera. We talk about the megapixels, right? We talk about pixels. What the heck is a pixel? Well, that chip that we have that we're detecting, the light, it's broken up into small little chunks, separated into small little portions. And each of those portion is one detector. So the more pixels you have, the more places, the more resolution that you have in your picture. So today, we have like 10 megapixel cameras. So we can 1 megapixel is 1 times 10 to the 6th pixels, roughly. So that's a very big array, and this isn't even, today this would be considered a cheap, inexpensive, and an unimportant camera detector. Much bigger than that. I also should point out that the filter that we use, we have red, blue, green. But you notice we have more green filters than we do red and blue. Anybody know why? The eye is more sensitive to green. Why is the eye more sensitive to green? Humans evolved on Earth. Look around. What do we see? We see a lot of green. So as a species, we'd like to be able to see green because often that's what we're eating. And so it turns out that images that we see, we'd like to see green. And so when we collect this information, we collect more green than we do red and blue. That's also why I have a green laser. Okay, all right, so what's the tie here? Well, so these detectors that are used in cameras, they're called CCDs, and there's another acronym, charge coupled devices, or CMOS, complementary metal oxide semiconductor detectors. These are all these acronyms that we use. But this was invented by Bill Boyle and George Smith, who were formerly working at AT&T Bell Labs in the early 60s. They were trying to make a picture phone. Well, guess what? Now we've got them. So they were way ahead of their time, but they won a Nobel Prize in 2009. Well, they won half a Nobel Prize for their, and the other half of the Nobel Prize went to Charles Cow for his work on development of fiber optics. Fiber optics. I'm going to talk about fiber optics now. So you take the picture of the bear, the microprocessor turns the image that we collected from the CCD array into current, into electrons. The microprocessor sorts them and puts them in a way that we turn them into zeros and ones. And so now there's this big file of information of zeros and ones that represents that picture of a bear. So now what happens? How does that information get to the data center of Facebook? Data centers of Facebook. Well, we know that there are these cell towers. Okay. So our phone, by radio, microwave actually, connect up to the cell towers. Okay, that's great. What happens then? Have you ever noticed these cell towers? What's at the bottom of the cell tower? What's at the base of the cell tower? A little building. I call it the outhouse. There's a little building at the bottom of the cell tower, and that little building has no windows, has a door, and has an air conditioner. Because inside of that building is, I could call it essentially a mini data center. Inside in that little building, there's some computer servers that are gathering this information and now sending it out to where it needs to go. So the cell tower detects the signal, it comes down. By the way, if you ever look at these things, there's gigantic cables coming down off of the cell tower because it's really hard to detect these signals that we're sending there, and they come down on these big cables, and they come into this into the base, into this room, and this is where what I would say. Whoops! Oh shoot! Good job. I'm going backwards. Sorry. This is where wireless becomes wired, meaning we've gone from radio waves, but now we're going into something that's solid, but it's not electricity, it's light. This is where the internet starts, and it's basically, we're converting these signals into light that falls into the fiber optics. Whoa. So jumping ahead here, when I say going into the fiber optics that are buried in the ground all across the country, all across the world, under the oceans, in our community. You know, a couple years ago we had this expansion of our internet locally, and we were digging up all over the town and causing fires as they cut through. It was pretty interesting. This is all fiber optics. And so the fiber optics are what I would call the infrastructure of the internet, which was developed by DARPA, maybe one of the few things that DARPA did right. And what's interesting is originally the internet was just for scholars, just for academics. I don't know how we let go of that, but we did. Now it's everywhere. And so what I want to talk about very briefly here, because I've been going too slow, how this works. So I want to turn my electrical signals into light. So to do that, I need to use what I call an optical interconnect. So I've got, looking at this from sort of just functions, I have some source of data, and on my cell phone camera that went up to the cell tower. So these are zeros and ones. These are little voltages. I then have a laser. The electrical signal is fed into a device called a light amplification by stimulated emitted radiation, or a laser. I should mention that once upon a time they thought about calling it light oscillation by stimulated emitted radiation. That would not have been a good acronym. So I'm glad they came up with laser. So it goes into the laser. The laser turns the electricity into light. In this case, 1.3 or 1.5 microns of light. That light then is launched into an optical fiber. Turns out that light can travel down an optical fiber literally hundreds to thousands of kilometers without attenuating. Much, much further than we can send a current pulse down a power line. So it's far, far more efficient. The other thing is that optical fiber can take more than one color. And those colors all are propagated down the fiber all at the same time, and they don't care about each other. That's not the case about electricity. If we put multiple channels of current into a wire, well, it just becomes more current. All right? So this is the key reason that we can send so much information down these fibers. First of all, the light can travel many, many, many hundreds of kilometers without having to be amplified again. And second of all, we can send a lot of different colors. Today, most these long-haul systems have 160 different wavelengths of light all going down a single fiber. And then in the bundles, they'll have literally hundreds of fibers. So you can see, and in each of those colors, we're sending data at rates that are mind-boggling. A terabit, 10 to the 12th bits per second. Huge amounts of data down these fibers.
What's the diameter of the fiber?
The diameter of fiber can vary. Typically, the business part of the fiber, the core, is about 50, well, for these long-haul systems, they're about 8 microns. For the kind of fiber interconnects in data centers, they're usually about 50 microns. Now, both of those numbers are small, but it's just a really simple thing here. 8 microns is really small, and in order to align, because we've got to get the laser launched into the fiber, in order to align that, that's a really challenging problem. On the other hand, if I have 50 microns, that's not so challenging. So if I have a tractor and I have a big barn door, the bigger the barn door, the better, the easier it is, the cheaper it is for me to get the tractor inside the barn. So for data centers, I want really low-cost technologies. I want to make it really easy to align. For long-haul systems like across the oceans, it's so expensive to deploy that system that I don't care how much it costs to build a component. It's still more expensive when I deploy it. So cost is no constraint. All right, and then when the light gets to the end of the fiber, it's detected, converted back into electricity, everything is wonderful. So a few words about the laser. This is one of the key parts of this because the laser is what turned the electricity into light that we could put down the fiber. Well, in 1962, there were 4 groups around the world that first reported, well, within a month. You know, 1962, we didn't have these instant communications. So a month was, for all practical purposes, instantaneous. There were 4 groups here, and I've shown their names here. Notice I got 3 guys here in black and white and 1 person in color. Why is that? Well, this person is Nick Holonyak. Nick Holonyak is one of our Professor Emeritus here. He was John Bardeen's first graduate student. So there's the connection. The guy who invented the transistor, his first student was one of the individuals who first demonstrated the semiconductor laser. But there's another reason why I show him in color, and that is, if you know Nick, he's got his way of thinking. Nick wanted to see the light, all right? These 3 guys, they were all making infrared wavelengths because even in the early 60s, we knew that we kind of wanted to use this from fiber optics, and so we knew the kind of the wavelength regime, and also the materials they were using was laser. But not Nick. Nick was like, I want to see the light. So this is a picture, not of the original laser, but of an early laser, and you can see the light. His contribution was he made the first visible laser diode. And in doing so, he used alloys of semiconductors, which, and then when a laser didn't work, it would still emit light. So this is one of the first light-emitting diodes. Light-emitting diodes now today are very important in our white lighting. And so Nick, simultaneously, sort of did what we needed to get done in terms of making lasers at different wavelengths and also establishing the technologies for light-emitting diodes. All right, I'm going to finish up here very quickly. So the laser, if you're going to make a laser, you need 3 ingredients. You need something to generate the light. We use a semiconductor. My favorite semiconductor is called gallium arsenide. Half of it's made of gallium, the other half is made of arsenic. And we put that together and we get this material that emits light. I need to excite this material to make it emit light. I can use current. So we use John Bardeen's p-n junction in order to generate the photons inside of this semiconductor. So I got my light. But now what I really have at this point is a light-emitting diode. I just have something that's just spurting light out everywhere. I want a very specific kind of light. I want stimulated emission. I want light that is all the same color. So to do that, I put this thing inside of an optical cavity, which is just a way to trap light. So I put 2 mirrors, 2 plane mirrors on either side, and you can think the light can bounce back and forth. Well, it bounces back and forth through here. This medium is generating light. It's also stimulating more light. And what do I get? I get a laser radiation. In this case, it's green, but that's how we make these, that's what we need to make a laser. So in my group, we work on vertical cavity surface emitting lasers, or VCSELs. These are very, very tiny little lasers. We make them by essentially manipulating the layers of a semiconductor wafer. And so if I took, this is an 8x8 array, this is an array of VCSELs. Each of those points is a laser. Each laser is maybe 10 microns in diameter, so 1/10 of the diameter of your hair. This chip is 1 millimeter on the side, so it's really, really small. If I was to break this and I look at it in cross section, you'd see something like this. These are just different layers of semiconductor. And I think you can see the dark layers right here. Those are what we call the quantum wells. Each of those dark layers is 8 nanometers thick. That's about 20 to 30 atomic layers. 20 to 30 atoms thick. That's the business part of how we generate the light. And by the way, Nick Holonyak invented the term quantum well. So we use quantum wells in our lasers. So my students are involved in research in my group. We are using these little lasers for a lot of different applications. One application is for interconnects in data centers. One application that's sort of come and gone is, how many of you had or have a laser mouse for a computer? Yeah. Well, the laser in that laser mouse, that's a VCSEL. And in fact, that particular kind of VCSEL that's in that mouse was something that I helped develop and invent when I previously worked at Sandia National Labs. So, and the reason why it's important for a laser mouse is because it's a very tiny laser, doesn't take a lot of current, you could use a little battery, and it lasts for, well, maybe a month before it dies. All right, so here's my last couple slides. This is some action pictures of my students. Here are my students standing in front of the facility here, over here in the microelectronics lab, working in my research lab, trying to measure and characterize these devices. We also make these devices, so I mentioned that we have a clean room. So in these funky gowns, which basically keep all of the human dust off of our tiny little semiconductors, we fabricate them. What do we fabricate? Well, let me just show you a couple pictures. These are, we're really interested in not making single lasers. We like to make lots of lasers. And we like to make arrays of lasers. So here's an example of some recent work. Oh, that's sitting right on top of that picture. Oh, well. Here's some arrays. And I think the point I want to make here is that you're seeing various images of things. You might notice some tiny little holes here. Those holes are about 1 to 2 microns in diameter. So all of this stuff you wouldn't see with your eye. Well, if we had a lens, we could focus the laser on your eye, which is not necessarily a good thing, which is why in my lab, all the microscopes have no eyepieces. They all have television cameras so that my students can't image the laser right into their eye when they're studying them. All right, so I'm pushing time here. So let me summarize and say that photonics enables what we call the necessities of modern life. I'm excited about this research because, you know, LEDs, charge coupled devices, lasers, and of course my favorite VCSELs, these are all technologies that not only are of interest in and of themselves, there's a lot of interesting microcavity physics in these devices that I couldn't possibly start talking about today, but sort of thing that I can get graduate students excited about to learn the science behind engineering. But once we know that science, we understand how it works, then we can start applying it to things. It could be as boring as a laser mouse that moves a cursor on a screen, and it could be as exciting as having, where we're working on electronic steerable arrays. So a little chip that the beam can be diverted different directions. There are a lot of applications. One of them is in self-driving cars. That in these self-driving cars, you're going to need a lot of sensors. You need a lot of electronic means for determining what's around you. And one of the approaches is going to be to use light. They call it LiDAR. It's the use of light for detecting the things around you. So let me finish by mentioning, Scott failed to mention, in addition to being, part of my responsibility as a faculty member is I do teaching, I do research, I also do service. And service can come in different ways. This example, one kind of service. But part of what I'm doing is I'm currently the president of the IEEE Photonic Society. So the IEEE, I'll say a little bit about this in just a moment, but the Photonic Society is a group of about 7,000 professionals who are all organized and all interested in basically using light for engineering applications. So there's a lot of different, why doesn't the website show up? I mentioned this, that if you go onto, if you're Facebook or Twitter, you can follow us, the Photonic Society. There is a lot of outreach and general information that can be found here. And we have over, I think, 50,000 followers, that, which is far more than our membership on this. This is my last slide. The last slide is about engineering. So the IEEE stands for the Institute of Electrical and Electronic Engineers. This is the old, well, I don't know if it's the oldest, but it is the biggest professional society in the world. It was co-founded by, the inventor of the light bulb, Edison. Co-founded by Edison, and
That's old technology.
yeah, okay. So it's an old, venerable organization. Within the IEEE, there are 42 societies, one of which is the Photonic Society. I say that because that hopefully kind of projects how broad the discipline is, how broad electrical engineering is. It is very broad. Furthermore, on this website, if you go to the www.ieee.org and you search under engineering or try engineering, a page will come up, and this is an extremely exciting page which has a lot of resources for teachers, for students, for parents, to basically try engineering. What does an engineer do? You know, there's sometimes a perception that, you know, we just walk around with our heads in the clouds thinking, spouting math, which is sometimes true. But there's another side of this, which is, you know, what we do is we solve problems. We solve problems that are important to society. And we've got some few problems coming now and future problems that we really need a lot of smart people to work on this. So anyone here who is does not have white hair, think about looking at this webpage to learn about electrical engineering. So with that, let me stop, and I'm sorry for going a little bit long, but I appreciate you coming out today and hearing a little bit about photonics and how it's important in your lives.
Thank you. So we have time for a few quick questions. If
one over there.
Like, can we see some hands?
She's dying.
Right here. Oh yes, I'm coming to you.
My granddaughter just became a kindergarten and preschool teacher in Chicago. Are there lessons or suggestions for her to be teaching physics?
So I am a proponent that, I was talking to my unborn children physics, and it bored my wife to death. I don't think you can ever start too early. One thing about photonics is that, as we mentioned, it's light, and part of that spectrum we can see. So, you know, when we talk a lot about some of the things we do, well, they're so small you can't see them. You know, to explain it, we have to use quantum mechanics. So it gets kind of complicated. But on the other hand, a laser is something that you can see. And after this meeting, we're going to have some hands-on demonstration. That might be a little bit advanced for kindergartens and preschool, but I can assure you that any kid that can hold something wants to hold a laser, because it is such a cool thing, the way that light goes. Because if I should have done this, but if I have a flashlight and a laser, the flashlight, I won't even see it on this, but the laser I can see, and furthermore, I could be shining it on a building half a mile away, and it'd still be a small spot. That's one of the unique things. So I think there are things that you could do for your middle school. I don't know if if such resources are on this page, though.
So Kent does do a great deal of professional service. I'll give a plug to my competing society. Actually, Kent's also very active in the Optical Society of America. And if you use the internet and you Google Optical Society of America, it will take you to the website. The Optical Society has created little educational kits called light blocks, blocks with an X, because we're that cool. And they're really good for, I think, for grade school age kids. They come with little clear plastic optical elements they can play around with, and some eye-safe little laser diodes in there. And that's important. The pointer that Kent is holding, you wouldn't want to give to your granddaughter, because that thing, if you held it right to your eye, really is dangerous.
This is not.
The green one isn't?
The one I lost
Oh,
was not. This is iSafe.
That one's iSafe? Okay, so you have to be a little careful with that. If it's a red pointer, it's almost certainly iSafe. But the green one, some of the green ones are a little dodgy.
Right.
So,
Right.
the Optical Society. Yep.
Yeah, you said a bad word there.
I put the of America.
Yeah.
It's actually just called the Optical Society. We dropped the of America a few years ago because it's an international society. So, but it's still called the OSA. So, okay, more questions. I'm sorry, I don't mean to take Kent's time. So we have more questions over here. I'll come back to you in a second.
At one time, I was a network engineer, and I actually plugged in the fiber optic cables for short runs. And one of the things that was useful is that there are two ends to each cable, and there are two ends that you're supposed to plug in, but they're exactly the same. And the way you could tell which one you were plugging in is you'd look at the end, you'd see red light on one, you'd look at the end over here, and you'd see red light on the other, and you plugged them in where the red light wasn't, so that the light was going in one direction on one cable and one direction on the other cable. Is that always true? Can the light only go in one direction on a fiber optic cable, or can it go in both directions?
No. It can go in both directions. The fiber optic cables are not. I mean, they're a fiber optic is just a piece of glass, a tiny little piece of glass that is designed to transport light down that fiber. And it can transport many different colors, including visible. And so you're right, these fiber optic come in bundles. And so a bundle of 100 fibers. And the question is, well, my gosh, how do you connect to the right fiber? Well, on the other end, someone will put a red light, and then you'll see that red light and you know which one it is. But if you plug the red light on your end, well, then he or she would see the red light on the other end. So it can go both ways. And in fact, these fibers are there. When we talk about the long haul transmission lines, they are bidirectional, because again, photons are fermions, and what I mean by that is they don't care about each other. They just pass each other. They don't really care. Whereas an electron has a negative charge. Two negative charges want to repel. So there's a fundamental difference between current and light. And one of the advantages is light doesn't care about each other. It can go either direction. It can have multiple colors. It's just a highway. But it's a highway where there's no left lane or right lane. It's going in both directions because the photons can just pass right by each other. They don't care.
Is that common though in computing equipment, that that a single fiber optic cable might be used to transmit bidirectionally? It
can be. What that means is that what you connect to each end has to have both a laser and a detector, because you got to go both ways. Is it common? Most of this is a question of cost, and so there's a difference between what's the right solution versus what's the inexpensive solution that's going to be used. And so in many of these systems, it is a one-way thing where we have lasers on one end and detectors on the other, because they don't want to have the expense of putting a source and detector on both ends. But on the other hand, if space is a constraint and they just cannot cram any more fibers to go both directions, then they might use the same fiber going both ways. So there's the technology, then there's the economics that you have to take into account.
Gentlemen, we'll just take, by the way, just one or two more questions, and then we'll release you to the hallway.
Hi. So as the light's going down the optic fiber over a long space, long distance, how does the amplifier overcome the signal degradation?
That's the slide I pulled out. Let me back up a bit. I didn't show this slide. I put this slide in here because this slide has an equation on it. And if I didn't show an equation, I get no respect from my colleagues, especially my theorist colleagues. That equation basically explains why light is transmitted down the fiber. Okay? And it basically light is bouncing back and forth between the boundary of what we call the core and the clad of the fiber. That the fiber is actually made out of two kinds of glass. There's one kind of glass in the middle, and it's surrounded by another kind of glass. And we design these glasses so that it can transmit the light. Now, as it moves down the fiber, this light can attenuate, as you pointed out. There is another phenomena which is actually even worse, and that is that the light that we're putting down it, I didn't go into this detail, but we have zeros and ones we want to transmit. Well, what is a 0 and 1 in light? But what it is there's two light levels. One is, I could say on-off, but that's really not true. What it is brighter and dimmer. So dimmer and brighter would be zeros and ones. And so we have in time, we have a varying amplitude of light traveling down this fiber. And what we're sending are bits. So we might send a 1, and then a 0, and then a 1, 1, and then a 1, 1, 1, 1, and then 0. Who knows what the sequence is that we're sending. And so that signal has frequencies involved, and those frequencies can travel at different speeds. This is called dispersion. That's the problem that we're really working with today, that the attenuation is really not a problem. It's the dispersion, because we send zeros and ones at one end, but if they travel at different speeds, at the other end, that might revert and become a 1, 0, which is an error. So that's when you're watching the Bears play football and they're about to make a score, and then your screen freezes. That's because somewhere there's a screw up in the data transmission. So the way we overcome this is we use what's called amplifiers, as you pointed out. We can put another fiber on here that has materials inside of that fiber that can amplify the light. These they're called EDFAs. There's another acronym. Erbium doped fiber amplifiers. These were invented in about 1998, in the late 90s. This was when, boom, the internet exploded. Because up until then, we had lasers, we had detectors, but we had no way to amplify the light conveniently. So what would happen is we'd have a piece of fiber here, we'd put light on one end, it would travel, and when just before it got so dim we couldn't see it, we would redetect it, convert it back into electricity, then convert it back into light and send it on again. These were called repeater stations. And so when we deploy the cables across the oceans, every 100 kilometers or so, you'd have to put in a repeater. Well, the repeater was a lot of electronics, detectors, lasers, power supplies, and they're being dropped in the bottom of the ocean. So we really can't go down and fix them. So they had to be really, really good. They had to be, last forever. And they were really, really expensive. But again, the deployment of the system was far more expensive than the parts. That was where the amplifiers didn't matter. But now if I want to put these in my data center, this is the other extreme in terms of now I have way more. Within a data center, there are millions of fibers and lasers. You can't even imagine how interconnected these buildings are. And so cost is the most important thing. So they don't want to put a lot of amplifiers on those fibers because that's extra cost. But it turns out these EDFAs dropped the cost and basically enabled the ability to make data centers. So my long-winded answer is yes, we can build amplifiers. They're literally just another fiber that you connect up to this, and there's also a laser part of it, and you got to connect it up. By the way, the laser that's used in the EDFAs, that technology was developed by Jim Coleman, who was again another emeritus professor in our department. So you got to tie back to Illinois for that. It's really kind of amazing, and I'm humbled in that. When I joined here in 2000, the gods of photonics had, this is the university, this is the place. And so coming here was like, I was very, very humbled. It was because there's been so many great inventions and developments on this campus. I think it's safe to say that the world would be a different place if it wasn't for the University of Illinois. That's extremely easy to say.
Thank you, Kent. So actually, Kent, can I ask you to stick around for a while and answer questions? Because I think there are at least 5 or 6 hands yet to be answered, but there are UN rules about these kinds of things.
Yeah.
So I'd like to thank you all for coming. I'd like to remind you that our best and brightest students are going to be having some laser displays out in the lobby. So please feel free to filter around, stick around, hang out with us for a while, and Professor Choquette will be here to answer questions. Thank you all for coming out today. We really appreciate you being here.